Hello, welcome to another problem session. Today we have a problem in a coupled system situation. So in this situation there is a large block here. So you have and there's a small block that moves, and this surface is frictionless and this surface is frictionless. So we have a frictionless problem. Well, in a frictionless problem like this, normally you would just apply conservation of energy, conservation of momentum, things like that. But here, our problem is to find acceleration, and because we have to find acceleration, we have to go down the route of forces. Okay, so how are we going to find the accelerations of this? Our laws are, if you know, F equals ma, because fixed mass, so this F on m, and F on big M equal its mass and its acceleration. So these were law applied, but they are this expression is true with respect to an inertial frame. So for instance, if I were using a coordinate for this small block that was moving with the big block, then this would not apply. So imagine a coordinate system that's kind of attached to this corner and moving with the block. So this moving with wedge, not inertial. So if you apply there, then we'll have to really look at this problem from inertial frame. So here is inertial frame. So this, and a fixed O, which is everything is moving with respect to that. And we will be able to apply these using these axes. So that may complicate the situation, because as you can tell that you have, let's see, as the corner of this wedge is x, and the y is 0, those coordinates for this point, and some point over here on this guy, let's call it xy, and so this is the y, and the capital X is this, and small x is all the way here. So in this triangle, you can see this is x minus big X and y, and so there's a y, little x, and big X are not independent anymore. That's the constraint. So in this situation, we have a constraint. One of them is like the block doesn't come off the table, so this y is 0. That's easy, and that makes it ay to be 0 in that equation. And the other one is a y over little x minus capital X is tangent theta, which is fixed, because this is the wedge angle theta. That's not changing. So if you work this out, you can write it like y equals to x minus big X tangent theta, right? And I can distribute tangent theta. So this is another equation. So this so we can call this equation, this call equation 1, let's call it equation 2. But you can take a derivative of this and you can say Vy ddt of this whole thing. So Vx minus capital Vx tangent theta. And you can do another ddt of this thing. And so Ay equals to Ax tangent theta. So this is like a number 3, this is number 4. You can see this one made this y component 0, but this one actually relates both this and that. So it's this has to be a part of when we solve the equations. Okay, so that's one equation. So this will be our one equation, okay, so now we can try to equation for say little m mass. Well, you probably know that just direction matters right there. So at this instant, what are the forces? Little mg, this angle is theta, and from the wedge at 90 degrees comes in normal. And these are only two forces. And axis here is, this way is x and this way is y. So you can see that this direction, this theta, then that angle is theta. And so we need to get x component, y component with respect to this. So what do we get? For x, I get n. This is same as theta over there, because this theta is same as that. So this is minus n sine theta. That's all along the x-axis. So this is for the x is m ax, and so this is equation number 5. And along the y, so this along the x and along the y, I get n cosine theta minus mg equals m ay. So this is number 6. So I can just call these guys, because we're not going to use them, so just call this one, redo this thing. So we use a simple notation here. So this is the new numbering for the equations. And so for the wedge, what are the forces in the wedge? Well, this normal is from wedge. This was from wedge on block. So third law. So by third law, we should be able to say that there will be a force exactly in the opposite direction on the wedge of the same magnitude. So it will be, and then from the table you have another normal, let's call it n0, and then there is mg coming down straight down. So simplifying this this for the reference direction. So this is theta. Free body diagram looks like, in the free body diagram, all forces come out of this one point, right? So this is n in that direction, this n, and n0 in that direction, and mg in that direction, and we have x-axis this way for us and y-axis this way for us. So if I this was the theta, and so this was the theta, this was the theta. Okay, so now I have everything. So I can write down for x direction n this n. So for x direction n sine theta, n sine theta, and nothing else is along the x direction. So capital M ax, and so this is equation 4 now. And along the y direction I have n0, that's from the table, and minus capital Mg, and then this normal from the little block, which is negative n cosine theta, and because ay is 0, this has to be equal to 0. This is 5. So we got these 5 equations, 1, 2, 3, 4, 5, and 5 equations is 5 unknowns. 5 equations and 5 unknowns. And what are the unknowns? You have unknowns are going to be let's see, one unknown here, another unknown, another unknown, another unknown, and another unknown. So those are 5 unknowns and 5 equations, and so you solve them by process of elimination or whatever your favorite method is. So I'm going to work it out in the next few slides. So right now I'm going to pause and get a new slate and solve these problems. Okay, so I took time to do the calculation. So these are the equations I rewrote now. Okay, and then I focused on what I need to get, which means I need to eliminate the 2 normal forces. Okay, so I can't guarantee all of this is really worked out correctly because I just did it here, but then principle is simple. I just do this as a first step, and then I do this, and then I do this, and then I use these equations. I mark them where they came from. And then I use in here, and then I get pretty really complicated expressions, which looks like okay, situation is complicated. If you say ax, if this was not accelerating, then I put it over here, then I get another very complicated expression. So usually it's a good idea to check if I made any mistakes. So if the theta was like vertical 90 degrees, ax will be 0 and ay will be this will be 1, this will be 1, and this will be 1, and you cancel out this guy with that guy. So ay will be So when theta is 90 degrees, I do get minus g, which is correct. That's not the only check you can do. Maybe there are other checks you can do. Well, I'll stop here because the video getting long. So just to recap, that in the case of a coupled system, you have to be careful that your inertial frame is the frame you're using. The coordinate system is not tied to one of the blocks or one of the objects which is accelerating. If the object is accelerating, then you have to use accelerating frame equations of motion, which are different than F equals ma. Okay, and that's covered in another chapter in some other time. We'll cover that also, but right now best to stay with a situation where the frames are not tied to accelerating objects. So when that happens, we are in this problem, we have this constraint that shows up, plus there's a constraint ay equal to 0. So these are the constraints, maybe called zero equation. And then we develop these equations of motion, and then we just go through the calculation. There is nothing really illuminating about this. The most illuminating part is to be able to get the constraint right. Okay, talk to you later in another video. Bye.